right, well, it's 4:02 now, so I think we could get going. So it's my great pleasure today to introduce Professor Alex Frañó, who is a professor at UC San Diego. So if you read his biography on the flyer, he has a ton of accolades that I could mention. So he got his bachelor's in physics from the National University of Honduras. He then, interestingly, did music in Mexico City, which sounds cool. So, right, you don't always have to go straight on to grad school. You can do some other fun stuff for a while. He then received his master's in physics, I guess, in Germany, correct, at the University of Stuttgart, before attending the Max Planck Institute for Solid State Physics in Berlin, where he received his PhD. He then had a UC Presidential Postdoctoral Fellowship at UC Berkeley. So he did a postdoc at Berkeley. And now comes to us from UC San Diego. I'd like to mention he also recently received the Sloan Research Award and the Cottrell Scholar Award. And Cottrell actually also helps to fund this seminar. So that's extra great, and thanks to them. So thank you so much for being here today. I'm looking forward to your exciting talk.
Thank you, Alex, and thank you so much to the organization committee of this seminar series. I want to say that I believe strongly in CalBridge. I think it's a fantastic effort, and I actually am honored to be a part of it by virtue of at times mentoring students or serving in committees and stuff like that. I think the mission and approach of CalBridge is fantastic, and I am happy to be part of it. So this one seminar series is another example of how what a good idea and how well executed everything is. So kudos to all of CalBridge and the organization committee. So today, this is a talk which is a little bit more broad than a science talk. In other words, I'm going to talk to you a little bit about my journey through this whole thing. And the title of my talk shows you a little bit about what I want to tell you, which is my personal and individual and highly unconventional journey through a topic of physics that is also an unconventional, which is unconventional superconductivity. And I'm going to show you how sometimes being, not fitting in can be a good thing, and how maybe you can even potentially use it as an advantage. So this is kind of what I'll tell you in some sequence, logical sequence. And first I'm going to introduce to you again who I am, why I'm giving this talk to you, and discuss a little bit about that trajectory. Then I'm going to tell you about superconductivity, which is the phenomenon that I am most fascinated with. And I'll tell you even more interesting is the notion of unconventional superconductivity, which is, in my humble opinion, one of the greatest mysteries of our time. Of course, that's a biased opinion, but here I am investing a huge amount of my intellectual effort working on that physics problem. So I suppose I should believe it's something very important. So let me start a little bit about my journey. So I was born in the country of Honduras, located down there. It's a very small country. It now has in the order of 9 million people. So it's a tiny little country in terms of population. And in terms of resources, unfortunately, it's even more small in the sense that we don't have a lot of resources there. In most certainly things like science and, STEM, if you will, broadly defined, as something that is not particularly well-funded, well-supported, etc. Let me give you the best example of this. I studied my bachelor's degree in the National University, the only university you could study physics in the whole country. And throughout the duration of my entire undergrad years, I was the only single student of physics in the entire country. So again, one would say, oh no, that's not great. But it turns out that then my undergrad classes were basically a tutoring with a few professors that are back in Honduras, have done some work outside and what have you. and then now have come back to Honduras, and they were glad to be able to teach physics to somebody, because other than me at the time, there wasn't any students. So it became a huge advantage to learn physics one-on-one. And I thought, and nowadays it has grown a little bit. Now there's in the order of maybe 20 students of physics in the country. And just as a reference, UC San Diego, my university where I'm faculty now, has about 400 students of physics. So, if you were to compare Honduras, maybe you want to compare it to the city of San Diego because of the size of the population. And you still see that it's a very small fraction of students who study physics. And that's yet again because there's not a whole lot of infrastructure, and people don't even understand what you could do with a career in physics, with a bachelor's in physics and so on. So that was the first sort of challenge or circumstance that I found myself in, which was quite extraordinary, right? But I also have another interest in my life, which is that of music. So after some time, after getting my bachelor's down there in Honduras, I've immigrated to the city of Mexico City, where I spent almost 4 years pursuing a career in music. And after that, I even spent some time in Los Angeles, also pursuing my career, actually pursuing different kinds of careers at this point. The music thing was kind of not working, but I had to keep going and found other ways of, surviving and, just bouncing around a little bit, and a lot of confusion. Those faces you see there reflect my state of, consciousness over many, many years. And so a total of 8 years went by in which I was completely not fitting in anywhere. And I tried many, many different things to do. None of them had anything to do with physics. Many of them were very sort of, hard labor kind of things. And many, many times during the course of these 8 years, I found myself completely lost in not knowing what to do. In the meantime, like I said, I worked in many, many capacities from washing dishes to translating to people, because I happen to know 2 languages, Spanish and English. And in that process, which was not related to anything academic, I learned a whole lot of lessons, life lessons, about how to treat people, about how to work in groups, about how to work in teams, about how to ask things from people, how to be courteous, how to interact on different levels. So many things that I believe turned out to be huge assets when I eventually landed into academia. So the sort of lesson I'd like to point out here is that bouncing around like that taught me incredibly valuable lessons that I believe make me much, much better at what I am today and moving forward as well. So after that, I went back to Honduras and decided that I wanted to go back to grad school. In fact, it was sort of a pipe dream of some kind, because I took a GRE that was terrible. In my defense, I had not done physics in 8 years, but I still would have never gotten a good GRE score. It turns out I'm a terrible test taker. So I had low GRE score. My grades weren't fantastic. Plus, I came from a university that really nobody had ever heard of. And my letters of recommendation and things like that were kind of meaningless in some sense, because you could, if you don't know where these people come from, the letter writers, it's hard to really make a judgment about who my potential. So this is something that many of you, I suppose, have or could face, which is that of, when you don't come from a very, elite and quote unquote university, it's not easy to get that recognition. And that's a very difficult challenge, right? Because you don't have that sort of, big name behind you. And for me, that was an incredibly hard obstacle that led to a complete widespread rejection across all of North America, including US and Canada. All universities I applied to rejected me. And most of them I was rejected by virtue of some automated email that was like completely, bland. At that point, I had to find another way. And what I discovered is that in Germany, they are open to foreign students because they have realized that the US's model of bringing in immigrants and foreigners from different countries is actually a good idea. So what the Germans had done at the time was start giving their courses in English, such as to attract non-German students, right? So in that sense, I ended up moving, just basically maneuvering almost. I'm going to use that word because it was all kinds of, it was not straightforward to get into a master's program in Germany. But at the end of, in the process, I just move around the world, finding these opportunities based on, coming from the fact that, when you come from a not so recognized institution, country, what have you, things are a little bit more tricky. And you have to navigate in some kind of different, you have to take sort of different alternative approaches. And that's certainly what I did. I also want to point out, Germany doesn't even care or doesn't even do GRE or any of such standardized tests, which of course was a good thing for me because as I told you earlier, I wasn't all that good of a test taker. So they accepted me in the city of Stuttgart. So I did my master's in this city here in the south of Germany. I did a 2-year master's here, and then after that I transitioned to the city of Berlin here to do my PhD. So I spent two years in Stuttgart doing this master's, and then I spent another 4 years in the city of Berlin doing a PhD. Now, you see again this face of confusion here, because quite frankly, I still didn't know where I fit. During my grad school years, I did what I did what grad students do, which is, you do a little bit of research and you publish some papers and you write in a thesis, you try to make it nice, et cetera, et cetera. And, but to me, that was just a job, really. I was just doing what I was supposed to be doing. I was happy to be living in Germany, happy to not have to live in Honduras at a time where the country was marred with extremely high crime rates and difficulties of that nature. And so I was just happy doing this, but still certainly figuring out where to fit in. Incidentally, I'm showing you this here. This is where I did my research, this facility here, that I'll discuss a little bit later what kind of facility this is, but this is called the Synchrotron, which again, I'll explain in a minute. So after spending some time in Berlin, I decided to do what's called a postdoc. For those who don't know, a postdoc is like a multiple year, maybe 3 to 4-ish years of postdoctorate, obviously. And I did that in Berkeley, where you basically just conduct research at this point. You don't have to take any classes or anything of that nature. You just conduct research, and ideally you will write some papers, publish some peer-reviewed papers. And then after a few years in Berkeley, still trying to figure out where I am, what am I supposed to do in this world, and quite frankly, what I'm good at. And after some time, my postdoc advisor tells me maybe you should apply for faculty jobs. And to my surprise, I somehow ended up getting an offer from UC San Diego, which of course is not only a beautiful place to live in Southern California, broadly speaking, but also San Diego in particular is quite beautiful. The university is incredible. And, one could say I'm done, I made it, I'm here. But to be very honest with you, I'm still figuring it out. In particular, I'm always trying to figure out how I fit in with my own experiences, with my own lessons that I've learned, and the attributes that I bring, precisely because I don't quite come from a linear trajectory. So to me, that is almost an asset of some kind. So why all this uncertainty? Why don't I just know what I want to do? I actually have learned that not being or not having a conventional path is a good thing. And like I said earlier, I believe that you can learn things that you wouldn't otherwise. So in some sense, I have made this asset, they made this an asset. Not being from the conventional path has become for me something of value. In other words, we all have advantages of some kind and disadvantages of some kind. And you can always find both in every circumstance. What I have grown to appreciate is that it's useful to understand this in your own circumstances, use it, either the advantages or the disadvantages that you have, and work on them, especially the disadvantages. Nurture the advantages and try to see how you can work around the disadvantages. I'll give you an example. For many of us in academia, you get comments of the kind that reflect some form of low expectations because you are who you are or you come from where you come from. I'm sure you've seen comments like this. You're a great student for growing up in a poor country, or for being a minority of any kind, etc. Right? So you've probably heard this, and this is it kind of stings a little bit, because you don't want to be seen as somebody from XYZ situation that is less fortunate. But at the same time, these are low expectations that people have about you. So I learned one thing at one point. I said, you know what? If people think that I'm gonna bomb this, I'm not gonna be good at this, then it's easy to overperform. Low expectations, then you just have to do it right, and then you'll be overperforming. And it turns out, life, generally speaking, in every aspect of life, it's always better to be overperforming than underperforming. So in some sense, I said to myself, you know what? Believe that I won't do it right. Believe that I'm a minority that comes from a very poor country. Believe that. Lower your expectations as much as you can. Now watch this. And that approach has actually helped in some way. So in a sort of weird way, I feel like these things can even be somehow used as an attribute. So, but anyway, I mean, I am at the end of the day, I do have a job, I do conduct research, I have an idea of what I'm doing. And that is basically research in experimental condensed matter physics, namely magnetism, superconductivity, and things like that. So this is a brief rundown of how the research in my lab works. You basically think about new materials, and we grow them using something called layer by layer growth. Then we measure some of their properties in synchrotron facilities around the world, which all of these I'll discuss a little bit more. And then we analyze the data using code like Python. And then we kind of repeat this over and over, and then eventually publish papers on that. I want to give a shout out to the folks that are members of my group. Actually, this was recently taken, but not all of the members are there for XYZ reason. But the list here is the current list of people in the group. And you see some visual of them there. So now I want to switch a little bit to physics. And I want to start by asking some, I guess, rhetorical questions, because I'm sure you can't really interact here because of the format of this, but it's okay. So let's discuss some physics. And I'll start by asking you, what is the difference between a metal and an insulator? Well, let's think. If I take a metal and I plug it into the outlet, electricity will flow through it. And if you're not careful, you can even get electrocuted, which is something we avoid all the time, using precisely what materials that are insulators, right? So you can take gloves, for example, that are insulating, those rubber gloves, and then you wouldn't have to worry about electricity flowing through you, because the insulating property of the gloves would protect you from electricity. So metals basically transport electricity, insulators don't. And that's the question, the answer to my second question. How do we transport electricity? Well, through metals. We use metals like copper. We use metals like, copper is a very common one because it's cheap to make. So all the wires in our grid, in the electrical grid, are made out of copper. But of course, you probably all know that there's something called resistance, which means that this process has loss over many, over transporting electricity over long distance. You actually have a lot of loss into heat and different processes. And so it would be better if we could find something that doesn't have loss. And this is what superconductivity is about. It turns out there are materials that were discovered way back about 100 years ago, 1911, in which if you plot, this is the y-axis here is a resistance, the electrical resistance of the material. And in the x-axis, you have temperature. Turns out that if you plot a normal metal, if you just plot the resistance as a function of temperature, it just sort of goes down like that and it saturates at some value. But you still have some resistance even at low temperature. But a superconductor is different. You cool down and the temperature and the resistance is lowering, but at a certain critical temperature, Tc, the resistance drops to exactly zero, not approximately zero, exactly zero. And this, of course, makes things very interesting because you can imagine that this could be the potential for new kinds of electrical grids and all kinds of stuff like that. And so this is, let's say, one of the first and the key aspects of superconductors is that the resistance is zero for temperatures below that. And it's also something called a perfect diamagnet, which means that it expels all magnetic fields in a very efficient and even perfect way. And this is actually something called the Meissner effect. And I'm going to show this to you shortly, but I want to point out that you can actually destroy superconductivity by obviously warming up. If you warm up above the temperature again, it goes back to the state here. You can also apply a magnetic field, or you can also apply currents. But what I want to show you, this is business of expelling magnetic fields, right? This is actually, I'm going to show you a video that I recorded not a long time ago, a few weeks ago, using a superconductor. So watch this. As you can see, this object carrying a stormtrooper is, of course, flying. Perhaps you can appreciate that there's nothing between the object, this black object, and this rail down here. It is indeed floating. And that's actually a virtue of this expelling the magnetic field. So these rails here, the rails that you see here are magnets. And inside this black object, this black box is a material that is superconductor. So because of this feature of expelling all the magnetic fields, you could actually work it out. And it turns out that it creates a sort of a counterforce to the effect of the magnetic field. And you end up with a levitation, actually. And then you can basically think of this as a way to produce all kinds of things like trains and anything like that. And that is superconductivity, and that is why it's so interesting, because it doesn't only offer you lossless resistance, but it also offers you abilities, things like this that are, otherwise impossible. Notice that there's sort of vapor coming out. That's because it's cold, and that's the downside of all of this, is that you have to keep the material cold in order for it to be superconducting. If you raise the temperature above that transition temperature, then you're back to where you were before and it won't float anymore. So the quest is to understand this phenomenon of superconductivity, and maybe we can engineer or come up with new materials that could be superconducting at higher transition temperatures. That is one of the major goals of this research field. So let me tell you what we do know about superconductivity. There is a theory created in, almost 50 years later, after the discovery of superconductivity, that explains what's called conventional superconductivity, in which electrons actually pair up into things known as Cooper pairs. So basically, two electrons become a pair and they kind of move around as a pair. And that is mediated, as we call it, through lattice vibration. So let me explain to you more or less how this works. So when you start off, the lattice of a material has vibrations, but when an electron comes close to some atoms, it attracts some of them and it creates a positive cloud. But a positive cloud attracts another electron because the cloud is positive, and then an electron is negatively charged. So then here comes another electron, and then these two electrons move in sort of synchrony across the material as a pair. And this theory was very successful, and it predicted that basically there was a high limit. There was some kind of high limit to the transition temperature of materials. And using this theory in 1986, it was predicted that the highest transition temperature would be 30 degrees Kelvin, which is not that high. You can imagine that's pretty close to absolute zero. That would be it's hard to cool down things to that temperature. So this theory here, this conventional theory, was only able to predict, or predicted only, materials to be superconducting to around 30 to 40 Kelvin. Over time, I'm plotting here, this is year versus the discovery of, this is the transition temperature of certain materials. So you have here a bunch of materials, and you're seeing the year they were discovered to be superconductors and the critical temperature of those materials. So you can see that this was the very first superconductor discovered, mercury, in 1911, as I showed you. And then over time, people have found different other materials, and the transition temperature TC keeps kind of rising. But the limit of this conventional theory says that all materials should be around this level right here, 40 Kelvin, right? It turns out that around the 80s comes these family called the copper oxides, which I'll explain to you what they are in a little bit. But basically, you have all these materials that have very, very high transition temperatures. And then about 20 years later, there's another class of materials that are like called iron-based superconductors, which also have high temperatures. And very recently, as in the last year, some people have discovered that under high pressure and under very high pressure, you can get also very high transition temperatures. So as you can see, there are the conventional theory has limitations. And so it is necessary to come up with unconventional thinking to describe the materials that are not fitting to that model. Now, let me tell you why these materials are so weird. It turns out, if you look at the periodic table, you can see here it's color-coded by virtue of whether they're magnetic or not. And in this side of the periodic table, all these elements are superconducting. All these blue elements can be superconducting at some temperature. And then the green ones under high pressure. But what I want to point out to you is that look at this row here in the periodic table, chromium, manganese, etc. This row here are not superconducting. They're white because they're not superconducting. If you go to this side of the periodic table, it turns out that this coding here reflects the fact that they happen to be something called magnetic. But the lesson I want to show you here is that superconductivity and magnetism just don't like each other. Just don't like each other, as was seen here, because these elements here are not superconducting and they are magnetic. So the conclusion here was, and there's a lot of research that shows that when it comes to conventional superconductivity, its worst enemy is magnetism, right? So it turns out that you can have, this is the kind of magnetisms that you can have in general. Magnetism, by the way, refers to the way that the electron spins in the material are oriented. So if you look at your refrigerator magnet in your house, it is stuck to the refrigerator because all the electron spins shown here by these arrows have a very well-defined orientation. So then basically the whole thing becomes like, each of them becomes like a little magnet, and all of them together become an object that you can stick to the refrigerator. There's also antiferromagnetism, where you have electronic spins pointing in opposite directions. But the bottom line is that these copper oxides that we also call cuprates turn out to be antiferromagnetic. So the spins are very much aligned, it just happen to be anti-parallel. But this here, in theory, should be the worst enemy for superconductivity. And this is the different kind of chemical ways to achieve this compound. These different chemical formulas, but I just want to show you that it turns out that all of them have in common a planar molecule, if you will, of copper and oxygen like this, and they're bonded like in these orbitals like that. And it turns out that the coppers indicated by these little arrows, like I said, are antiferromagnetic. So in theory, these should be very, very not superconducting. So if it turns out that if you take these materials and you dope what's called, you introduce something called a hole. So you basically change the chemical formula. Let's keep it simple. If you change the chemical formula of the material, you end up with something like this that is called a phase diagram. A phase diagram shows you temperature and this amount of chemical disorder, chemical doping, if you will, just to give you some easy to sort of grasp perspective here. And what you see here is, for example, this green dome here is the superconducting dome, where you basically have a TC, and the material is only superconducting for a certain composition, basically, below a certain temperature, okay? But more interesting than superconductivity is the fact that you have all these other so-called electronic phases around the superconductivity. For instance, here you have this antiferromagnetic phase right here. Here I have something called the pseudogap, which I don't want to get into. It's extremely interesting, very ill understood. And then here there's a strange metal, and I'm going to discuss a little bit about that. So in other words, I'm just going to walk you through all these phases, as we call them, electronic phases. So this region here where we have antiferromagnetism, as I showed you earlier, the electronic spins are pointing anti-parallel to each other, as shown here. So this spin, for example, is pointing up, so the next one is pointing down, and etc. And because of this, as I said earlier, this should not be a superconductor, yet it is. In addition, in this region right here, what happens is that not only do you have spin stuff going on, this arrow stuff, but you also have what's called the charge density wave, or charge order, which is basically a wave that forms in the electronic charge. So the electronic charge, as you know it, probably you remember it being a discrete thing, like the electronic charge is E, right? But it turns out that in these materials, it can form a wave. The electric charge forms a wave. In fact, and this is actually something that I've spent a lot of my research on, looking at this charge density wave, or charge order, or charge wave, as I described here. And I'm going to talk to you a little bit about that. So altogether, you have the phase diagram, and you have all kinds of fluctuating, as we call them, phenomena of both charge and spin and all kinds of stuff. And that's what really makes this material super interesting. I also want to tell you about this region here called strange metal, and you'll see why I find it so interesting. So I'm going to talk to you a little bit about this. And what happens in this region here is that the electrical resistance turns out to be linear as a function of temperature. Now you may be wondering, why is that interesting, right? Why is that interesting? Well, as stated in this paper here, which is not one of my papers, but it's a paper that is really great. It turns out, read this sentence and go to the last part. It says, this linear resistivity is a major puzzle of condensed matter physics. Furthermore, if you read this paper right here, which I find so good, by the way, it turns out that we quite don't understand this, because this linear behavior is not what normal conventional theories would predict. It turns out that basically what happens in that region is that the rate of dissipation between electrons slows down to reach something called the Planckian limit. And the Planckian limit is a result of something called quantum entanglement, which is believed to happen inside black holes. In other words, yes, you can study black hole physics in a piece of ceramic material that we can easily make inside a lab. And that's one of the key reasons why I find this research topic so fascinating, is because it's a lot more than just superconductivity, which is already an incredibly awesome phenomenon. The physics that give rise to this are so complicated that A, we have no idea, or we have some idea, but we're not clear yet. We haven't really figured out how these materials are superconducting. And the reason we haven't is because the complexity of this so-called quantum entanglement that occurs gives rise to some physics that simply are not within the grasp of our current conventional theories. So we really need new ideas coming from new people especially likely to come from people from not conventional backgrounds. And yes, like I said, if you're interested in super crazy black hole physics, you don't have to necessarily jump into a black hole to measure it. You can, conduct research in condensed matter physics and actually probe exactly the same kind of physics that happen or are believed to happen in black holes. Let me tell you another thing that superconductors can be good for, which is actually the subject of my current research as well. In my lab, we're actually trying to mimic the way that the brain works. That's right, I'm jumping from superconductors to brain functionality. As you know, our brain is made up of very simple things that, proteins and molecules. A protein eventually makes up a neuron, and then a neuron eventually makes up a brain. Now, this is something called emergent complexity, in other words, emergence, because one neuron alone will never give you the behavior of a brain. The brain functions the way it does because there is a lot of neurons and they make up a network, and the behavior of the brain cannot be described by simply adding up all the behaviors of the neurons. That is what the Greeks called emergent behavior, meaning the sum of the objects does not equal to the behavior. Rather, it is a new behavior that arises because of the fact that everything is sort of, entangled, I guess could be a good word. So on the other side of this graphic, so all of this is what happens in biology, but what we're trying to do in using materials is we're taking these cuprates that I mentioned earlier, and we're designing a crystal lattice, very well defined, and then we're making a device from them. And this is actually a very specific kind of device. And this is basically what you see here. Basically, we're using these superconductors to make a Josephson device. I don't want to get into the details of what that is, but what I'm trying to tell you is that you need it to be superconducting. So you can make one of these devices that turns out to function like a neuron. Okay, the device that we made out of superconductors has the properties of something called spiking that neurons also have. Well, as inspired by biology in our brain, if you take a network of these devices, it turns out that we have, there's a paper that we just submitted shown here, that the response of a network, especially a disordered network, you can see here that the devices are kind of randomly positioned. Turns out that when you have a lot of disorder in this network, we believe it has the emergent properties of the brain. So we're pretty excited about this, and it kind of shows you what superconductors can do that is just completely bizarre in the sense of, like, you started off with this low resistance, but it turns out to be much more complicated. And I've shown you examples of pretty wild things that you can conceive of from that. At the end of the day, as I showed you clearly, what superconductors can be used for is an open question. There's a lot of research that can be done on this topic, and a lot of it will come, the better ideas will likely come from people that are fresh into the field. And I believe myself that unconventional ideas will be needed to solve these problems and come up with good ideas. And those usually come from backgrounds that are not your conventional linear trajectories. Anyway, that's more or less what I wanted to share with you. I will discuss a little bit about where I conduct my research, because we're kind of running out of time. I wanted to show you this business of synchrotron because it's very, very cool. Synchrotron, I use X-rays to study these materials that I showed you. And to get these X-rays, we go to a facility called a synchrotron, where electrons, this one picture here is actually in France. These electrons are going around in a circle around this ring here. You can see the scale of this. These are cars here. And it's a huge facility. You have the electrons going around, and as they bend, you actually see, you actually get light from them. And so you get a beautiful sort of, you can use this X-rays specifically to study your materials. And so it turns out to require relativity. So you can see this picture inside this ring. there's this pipe here and the electrons are going in there, and they're going at speeds that are extremely close to the speed of light. And these facilities are spread out all over the world. So like I showed you earlier, I did my PhD in Germany. So there's facilities in Germany, other facilities in Europe, some in Asia, one in Australia, one in Brazil, and then in the US there's a few. And so our group travels mostly to, well, these are basically the facilities that we try to go to. So in some respect, not only do we carry out pretty awesome research, but we get to travel to these great places as well. So that's also something that our students find very, very attractive. And finally, just as a side note, synchrotron has been an important tool to develop or to understand the structure of proteins, the sort of microscopic structure of proteins. And there has been a whole lot of Nobel Prizes for this, and there's also a lot of work to be done on this. And even in the case of COVID, there was important work done at synchrotrons determining the protein structure of the SARS-CoV-2 virus. So synchrotrons don't only tell you things about superconductors. They actually have a lot of applications where people use these X-rays to study different kinds of substances, materials, molecules, etc. So in conclusion, I think and I believe that being unconventional, coming from an unconventional and disadvantaged place can be a good thing. And most important is you want to find your path. Important is that you're going to have to make sacrifices to get to this kind of situation. And so it's better, it always works better when your passion is, when you're doing what you're passionate about, so that you can, enjoy this process a whole lot. There's a whole lot of, difficulties along the way. So it's always better to be doing something that you really, really like and find fascinating. And in the case of this material, these cuprate superconductors are highly unconventional. And that's what makes them interesting. And among the biggest mysteries in all of condensed matter physics, I would even say, in my opinion, among the greatest mysteries in all of physics. And the research on this material spans such crazy kind of phenomena that include the physics of black holes, all kinds of quantum entanglement effects, and also in our latest research, we're trying to use this to do brain-inspired computing. So to finalize, this is who I am. If you're ever interested in either conducting research of this kind or learning more about this research or whatever, feel free to contact me. I'm always here to help. And I was a student as well. I've struggled. I understand how hard these things are, and I'm always willing to help in any way that I can. So thanks.
All right. Thank you so much, Professor Frañó. That was amazing. Such an interesting talk. That's so crazy that the neural networks and black holes, that's amazing. And thank you so much for sharing about your personal journey as well. I think so many students assume that everyone has this linear path, but it's really not true. So thank you for sharing.